All right, we're moving on to the next module, starting with lesson one. The opening exercise, kind of going through and what we notice is happening between each stage of the numbers. So there is a pattern of the numbers, and we just have to figure out what that is. So from my first number, 2.4, to get to 5.76, what I need to do to get that number is square it. 3.4 squared is 11.56, 4.4 squared, and so on and so forth. So if I square those numbers, I get my second row. So how do I get my third row? So I can see it's kind of in between these two numbers. So I want to figure out how I can use those two numbers to get the 5.8. And it turns out that if I subtract them, I get the 5.8. So let's see if that pattern holds up. 19.36 minus 11.56 is 7.8. 29.16 minus 19.36 is 9.8. That pattern holds up. That's awesome. And then again, it looks like I can go in between the 5.8 and the 7.8. And that's a little easier to see that I'm getting 2 on a subtraction. And 9.8 minus 7.8 is 2. 11.8 minus 9.8 is 2. So I have a pattern that gets me down where I have a constant number. So let's see if we can figure out using this pattern for 7.4 and 8.4. So I'm going to carry over 6.4. And then 7.4 and 8.4. So 7.4 squared is 54.76. And 8.4 squared is 70.56. And then I took the difference of the numbers. So 54.74 minus, 76 minus 40.96 gives me 13.8. And 70.56 minus 54.76 gives me 15.8. And when I take the difference of 15.8 and 13.8, I get 2. So I'm back to that constant of 2. So then it asks, how would I label each row of numbers in the table? So I'm starting off with my original number. And then I'm taking that number and I'm squaring it. And then I'm taking what we're going to call the first difference. Difference meaning subtraction. I'm doing it for the first time. And then I'm doing it again, so this will be the second difference. And it's these differences that we're going to use throughout this lesson, as they do play an important role in determining what degree the equations are going to be if we're working backwards, or how I can determine whether or not the degree of the equation is correct. So let's look at the sequence of first differences for a linear polynomial. If A and B are my constant coefficients, I'm going to have my first general polynomial for linear a plus b. My second would be 2a plus b. My third would be 3a plus b. And then if I look at the differences, 2a plus b minus a plus b leaves me with a. 3a plus b minus 2a plus b leaves me with a. Let's see if this pattern holds up. 4a plus b minus 3a plus b gives me an a. So the first difference for a linear is constant. And inherently, you knew this. That's the constant rate of change we always talk about with linear equation. So the ax plus b, the a is constant. That's what makes it linear. Now, if we take the second differences, a minus a is 0, 0. I'm going to get 0. There's nothing else I can get there. So the second difference is for ax plus b is 0. So once I've gone beyond a limit and get to 0, I know I have reached my maximum. So the first difference determines it's a linear. So let's look at first, second, third differences for ax squared plus bx plus c. Now hopefully we recognize this as quadratic because it's to the second power. So when x is 0, I'm going to have c. When x is 1, I'm going to have a plus b plus c. When x is 2, I'm going to have 4a plus 2b plus c, so on and so forth. I'm just plugging this column in for x into the equation, and then I'm going to subtract. So my first difference, if I a plus b plus c minus c, just leaves me with a plus b. Again, the c's will cancel, but this time I will have 3a plus b. C's will cancel again, but this time I'll have 5a plus b, and then 7a plus b, and hopefully you can see a little pattern forming. 9a plus b. So those are not the same. So we know first difference confirms linear. Let's see what confirms quadratic. So now let us do the second difference. I get 2a, 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 and 2a. So all the second differences are the same. They are constant. And when my second difference is constant, it means that I have a quadratic. And the third difference, again, 2a minus 2a would be 0 all the way down. So there is no third difference, but I have a constant second difference. And the constant second difference of a quadratic will always equal 2a. The constant second difference of a linear, or first difference of a linear, will always be a. So I can tell by the differences what type of equation I have, and this will become more evident when we get to an actual numerical table. But now we're going to check out what happens when we have a cubic, or to the third power. And again, we're using the numbers 0, 1, 2, 3, 4, and 5. I'm putting them in for x into these three places. So I end up with just coefficients of a, b, c, and d. And thankfully, they've done the first difference out for us. So now we're going on to the second difference to see if it's quadratic. I end up with 6a plus 2b, 8a plus 2b, 12a plus 2b, and then 18a plus 2b, and then finally 24a plus 2b. Still not constant, so let's go to the third difference. That's 12a, remember? So we have the b's will cancel out. 12 minus 6 is 6a. B's cancel out. 18 minus 12 is 6a. B's cancel out. 24 minus 18 is 6a. So I have a constant third difference, which verifies it's cubic. So you can tell the difference, the number difference, is equivalent to the highest exponent. So constant first difference, linear, exponent 1. Constant second difference, quadratic, exponent 2. Constant third difference, cubic, exponent 3. And I would get 0 if I did the fourth difference. And this pattern holds up. So if I wanted to do quartic to the fourth power, I would have a constant fourth difference. Quintic to the fifth power, I would have a constant fifth difference. And so based on this general formula, I know that the constant third difference of any cubic, this is just general, is going to be equal to 6a. And I'm going to need to use that information as I go forward and figure out what I'm going to do in this numerical example. And that's where we'll start the next video.